Hello and welcome back to Calculus 1, section 3.6, derivatives as rate of change. So this is where we start looking at some application of our derivative. We are going to take a look at the probably most popular application for the derivative, and that is measuring your speed, how fast you're moving. So there are two different speeds or velocities in this case that you can talk about. One is average and the other one is instantaneous. The average velocity is the velocity that is taking account all of the different speeds at which you went and averages them out into a single number. You obtain that value by dividing how far you went in the amount of time you spent moving. So, if you are going from, let's say, college to New York, there is 60 miles. Now I'm only going to count up to the bridge because after that it's just crazy. So you never know. You might never get to your destination. So up to the bridge or a tunnel, and that's it, right? So 60 miles, 60. That would be the distance that you are covering. And let's say that you are able to do that in 1 hour. You would calculate your average velocity by dividing 60 miles by 1 hour to get 60 miles per hour. Are you always going 60 miles per hour? No. You are going to go above, and when you hit the traffic or changing lanes and stuff, you're going to go below. So there is variation in your speed, and when all of those average out, they will average into 60 because it took you 1 hour to cover 60 miles. If it takes you 2 hours to drive the same distance, let's say there's some kind of light snow, well, if it takes you 2 hours, then your average speed would be 30 miles per hour. Is it always exactly 30? No. Goes above, goes below, goes above, goes below. But they would all average, right? So, do we use any derivative here? The answer is no. We don't use any derivative in this calculation. This is the secant calculation, the one that it's calculating just the slope of the secant line where you have your position function. Position function S of t. And to get this average velocity, you take S of t2, that's when you got where you're supposed to go, minus S of t1, which is your initial location when you started, divided by t2 minus t1, which is the difference in time, so how long you were driving for. So this is our calculation, and that's the average velocity to compute. Now you can compute the average velocity using that formula, and that's just a standard physics formula. However, we are interested in instantaneous velocity. That's the one you get ticketed for if it's to over the posted speed limit. Say the posted speed limit is 65, you are driving 66, you are going 1 over, right? So it's called speeding. So the speedometer on your car is the one that measures your instantaneous velocity. And that is what derivative represents. As soon as you touch your gas pedal or the brakes, even slightly, it changes. And it changes to a different value. So when you glance, that split second you glance and you take a look at what the speed is, you are reading the value of the derivative. So in order to calculate average velocity, you have to complete your trip. You have to be done with driving. You don't have to be out of the car, but let's say you have to be out of the car, and now you say, I left at 1:15, I got here at 2:15, I was driving 1 hour exactly, right? So you have the time. You can subtract the odometer before you leave. You wrote the number. Once you got there, you have the number. You subtract those, distance divided by time. So average one is very, very easy to compute. Instantaneous one is the one that it's a derivative. And as I said, only as you drive, that instantaneous velocity is measured and shown on the speedometer. So it measures your speed at an instant. Now, why is it called a rate of change? Well, aren't you changing your position? Right? You started here and you are going to end up in New York, so you are changing your location. You're changing your position in time. And change of position in time is called the velocity. So that's what we are working on today. So now, when I have a position function, s of t, right? S of t, position. You can give me the various values for t, which is time, and I can compute where I am at that time. So t equals, let's say, 10 for 10 minutes. I will be, let's say, 7 miles from here. Now, velocity function is calculated as the derivative of position function. And that's velocity. After velocity, if we differentiate one more time, we will get acceleration function, a of t. So that's the derivative of velocity. And if you were ever confused by this, we can use our calculus language of change to understand this entire sequence of events. Say you want to go from point A to point B, and you are at point A. You are stationary at point A. Are you ever, while standing still at A, will you ever get to B? The answer is no, right? So there has to be something to drive this change from A to B. And that is what?
Force.
Nope.
Right.
Velocity.
Okay.
So if you are at rest at A, then your velocity is 0. So you cannot change your position from A to B because you are standing still at A with 0 velocity. So now you need to change velocity. Now how do you do that?
Acceleration.
Acceleration. Your gas pedal in the car is accelerator. Your car, when you get into the car, is hopefully at 0, right? Because it's parked. You're not running next to the car and just jump in. So the car is parked. It has a velocity of 0, which means the car is not moving and it's not changing position from A to B at that moment in time. Your job is to introduce acceleration, and then acceleration, which we see is change of velocity. You will introduce the acceleration by pressing the gas pedal. Acceleration changes velocity from 0 to a number that you're driving at, and then the velocity causes position to change. You see, there's a lot of this change that it's happening. Now, you also change the state of acceleration as well. There is another derivative that you can add. It's called jerk, because you need to change the acceleration, right? Because your pedal is not pressed, right? So you experience jerk in the car when you push either gas or the brakes too quickly, right? You experience it. The rapid changes of acceleration and brakes are also acceleration, known as deceleration, so it's just negative acceleration. When you push gas pedal, your velocity is changing up. When you push brakes, your velocity is changing down. So both of the pedals, some of you have cars with 3 pedals, please update. We are moving to the cars with no pedals, so at least you can upgrade to the one with 2. No, but for the thrill of driving, really. If you want a thrill of driving, try to make a car that has like 15 pedals or 80 pedals, like a piano. All right, try to drive that. Anyway, so we start with the car that it's parked at the location. Location is not changing because there is no velocity. There is no velocity because no one pushed the gas pedal. Now, you press the gas pedal, which is acceleration. You added the acceleration. Acceleration is change of velocity in time. You know that, the car is rated to go 0 to 60 in 2.3 seconds, right? Great. See that 2.3 seconds? That is your time in which the velocity was changed from 0, not moving, to 60, moving at 60 miles per hour. So acceleration is change of velocity in time, and then the velocity is causing position to change because velocity is change of position in time. And then you're finally able to get places. Would deceleration make you go back to A? No. Deceleration reduces your velocity, and you can reduce velocity all the way to 0 and then just stop at some location. But no matter how much you push your brake, you are not going to go back to A. All right? Yes.
We're not going to talk about negative velocity, because I don't think physics, we're talking about
Well, you turn around the car, right? And then you can go negative. But or you can put in reverse and go negative. velocity has a sign. If you're moving with a forward direction, it's positive. If you're moving in a negative direction, it's negative. Where the speed is, see, velocity, we don't deal with vectors in this class. We redo this in Calc 3 when we deal with vectors. But if you take a physics course and enjoy physics course, then you have velocity defined as a vector, in which case you have a direction and you have magnitude. In which case your plus and minus are important in terms of which way you go, and then your magnitude is how fast you go, which is also known as speed. Now over here in calculus, since we are only moving forward, we can equate our velocity with speed, but technically speed is the absolute value of velocity. Don't do this experiment yourself. If someone else is driving, if they happen to put the car in reverse and drive, if you take a look at their speedometer, when they push the gas pedal to go back, the speed will still show positive value. So speed is absolute value of velocity. Now, if you are dealing with physics or Calc 3, we say magnitude of the vector. So we will not be dealing with the signs. So now, if I give you position function, s of t equals to, let's say, e to the negative x cosine x. So this is going to be specific type of motion that is studied in physics and differential equations and so on. It's oscillation with dampening because of this e to the negative x. We all know that cosine x alone is a wave that starts at 1 up there and then just goes like that forever, right? Now what e to the negative x is going to do is going to kill it over time. So the graph for something like this would be that. Oh, sorry, this is supposed to be t's because it's s of t. It's s of t. So you do see a cosine-like structure which is dying out in time as you move away. Now this is your path function. Where do you see this? If you have a pendulum, here's the pendulum right here, and if I swing and let go, I'm a professional, relax. And I just leave it. So me stretching it to the side is going to be that top point displacement where the graph starts at the time 0. And as I let go, every time when it returns to the right side, your right, my left, it will be less, it will go less into the air away from what we call equilibrium position, which is in the middle. So when I let go, as you can see, it very quickly, in maybe 12 to 15 of these right swings, it stays at rest. So this type of motion, right, is described by this equation, and then if you want the particulars, you will measure some constants and put negative 2t and maybe cosine of t over 2 or 2t or 5t, whatever. But nevertheless, that's the motion. And if I know the exact equation for a motion like this, I can compute, if you give me time, I can compute the location where the object is at any given time, which is why mathematics is so damn important if you are doing physics or engineering, because you are creating devices and you want to know where your stuff is, right at that point, whether you are dealing with motion or you are dealing with electrons or you're dealing with whatever you're dealing with. You just want to know where your system is. Now, you have equation for the position. You want to take the derivative of this, so ds dt, to find what we call velocity function. And now, to take this derivative, we have to do what? Product rule, very good.
Yeah.
You have a function e times the cosine. So you have two functions multiply, you have to do that. So copy the first times derivative of the second plus copy the second times derivative of the first. So that a business that we had, like sine ax and so on, you remember we had the one for e as well. So e to the at was a, e to the at. In our case, a is -1, so that's why the negative dropped down when we took the derivative of e to the -t. So now we can factor out negative e to the -t, leaving sine t plus cosine t in parentheses. And this would be our velocity function. So now you tell me that you want to know stuff about the object after, let's say, 2 seconds. You will plug in 2 for every t, and you will have position at 2 seconds, and you will have the velocity of the object at 2 seconds. You see, the derivative is measuring the velocity at the single point, right? If you get pulled over for speeding, is it taken in consideration that you were doing 20 below speed limit 2 miles ago? No. Is it going to be taken into account that you will be driving under the speed limit as you leave the right, as you leave the place where you were pulled over with a ticket on your seat? It's not taken in consideration, right? The only speed that was taken in consideration was the instantaneous one, the instant when you were measured. Instantaneous speed, the derivative speed, is the one that happens in a split second. And that one is the one that you get from the derivative. And that's the one that you can measure with this formula. If you want to measure the average speed, well, t is equal to 0. That's your initial speed. And then your final, t equals 0 seconds when you started with your position. And then whatever your final time is, let's say 10 seconds later. So you have your initial and your final position. So you can calculate how far you went, or the particle, or whatever. And then you have the time. You can calculate the average one as well. The derivative formula will calculate this. And then finally, we can take another derivative and figure out the acceleration. So derivative of velocity in time is acceleration. That's another product rule, but now it looks more complicated. Copy the first times derivative of the second. Derivative of sine is cosine t minus sine t plus sine t plus cosine t. And finally, the derivative of this is just e to the -t, because negative and negative cancel. So now I distribute negative in this parenthesis, which will swap the order, I have e to the t of sine t minus cosine t, and then plus e to the negative t of sine t plus cosine t. And when I distribute e to the negative t sine t minus e to the negative t cosine t plus e to the negative t sine t plus e to the negative t cosine t, the cosines will drop, and then we can factor out e to the negative t. Oh no, we just have two of these. So 2e to the negative t sine t. You can be given polynomial function, logarithmic function, square root function. It doesn't matter what your position is as a function, as long as you know to take the derivative properly. You will be able to take the first derivative and get velocity, take the second derivative and get acceleration. And then you will compute at the point that you're asked to compute at. Time after 2 seconds, time after 3 seconds, or whatever, right? So that would be the story of velocity, acceleration, and that stuff. Now, some of you enjoy business, right? Right. So how about we take a look at one application where we can make some business decision. We'll have more of this as the course goes on. This is only our first applied section, so it's cool to bring that in as well. So there are two types of people in the world, right? Those that know math and those that don't. Now, if you know mathematics, you have significant advantage in doing business, because you can make good business decisions because you understand not just the market but also which way the money works in terms of cost, revenue, profit, and all of that. A lot of businesses fail, and a lot of that failure is directly tied to poor business decisions in terms of money, which involves figuring out the profit, the cost, and everything else. If you are running a small business, yeah, maybe you can wiggle and somehow get it to work without being very literate. But large companies employ people that understand mathematics and do mathematics so they can actually make those companies profitable through policies, procedures, and so on. If it costs you $50 to make a product and you charge $40 for it, then clearly you are losing $10 per unit, and you are going to fold very quickly. If you are selling exactly at cost, your business is also doomed, because there will be no money through profit to fuel further development. You would still be on your iPhone 1, which hardly has any less features than the one you actually have right now. But the trick is that as a company, you must have profit in order to use that profit in research and development to develop a new product that will be competitive on the market so your company can still sell products and still exist. So it's very interesting to observe this new narrative of whole bunch of people your age screaming against profit and how immoral and terrible that is. Really? Really? So you have to understand that in order for any progress to be made, it's driven by profit, because the profit is the one that it's going to be used to hire new engineers, to hire new people that will develop the next generation of the product. Otherwise, competition will take you out. How many of you have a 10-year-old phone in your pocket? And there will be no one. I don't have to actually, right, do that experiment, right? So, understanding that profit is needed, you also need to understand that the reduction in cost is something that is very important. Less cost means more profit means better product, because you can invest more into development of the new products. The amount of money, revenue, which you collect from selling your products is going to be finite pot of money, and then you will subtract the cost, and the costs are usually great. You have the cost of transportation, cost of storage, cost of production, cost of materials, cost of buildings, and everything that is in those buildings, so you can run the business. And so the costs are great, huge, and companies are constantly looking to shave anything they can to save on cost so that they can turn larger profit, and when they turn larger profit, obviously they can do better. So now we want to take a look at the cost analysis of certain production. I would like to take a look at both average and instantaneous cost to produce some kind of goods. I don't care if it's a car or a fork, doesn't matter. My goal is to understand the cost for my company so that I can see if I'm going to be profitable. If I'm not profitable, there is no need to have the company, because I can't compete on the global market. So we are going to introduce, let's call this cost analysis. So C of X is known as cost function. And then you can take your business courses and learn about the variable cost and the fixed cost and all of these things that you can do to figure out the cost equation. In our case, equation for the cost is given, but there is a big market out there for mathematicians and people that understand business and math to create these types of functions. So, and they're well paid so that the companies can stay profitable and competitive on the market. So C of X will be the cost function. Now C bar of X is going to be the average cost to produce X items. And the equation for average cost, which is C with the bar, is going to be the cost function divided by the number of units you are producing. Now, this equation is really cool because it shows you that when you are making a small number of anything, the cost is usually large, right? Anything that it's very unique or has very little units produced has a large cost. Tesla cars, very few produced in comparison to other car giants. Tesla is very, very pricey, even though it is the best car in the galaxy, but still. Painting, an artist will be working on a painting for 6 months, and after the 6 months, this one piece of art is complete. It's put up for sale for $50,000. Does it make sense? Well, yeah. If this artist is going to produce 2 paintings a year, right? Then making 100K, right? So anything that you are going to produce one or little bit of, the entire cost of production and labor and everything is poured into those very few items. So their cost is high. Now, if you're going to produce these markers and you're going to push 1 million of them, well, I would be kind of iffy to buy it if this was $2,000 per marker, right? Which is why they're priced at 50 cents. The third cost-related thing that we are learning is a C prime of X known as marginal cost. And that's the one I'll put derivative. And this is the marginal cost is the cost of the particular single item. So marginal cost is the cost. Please make sure that you understand. I said the cost, the specific, the cost of a specific item. So I want to know what is the cost for me to produce the 100th marker. And how about 1,000th marker, 10,000 marker? If the business is set up properly, if the cost function and everything, right? What we are going to see is that if I produce 10 of these markers, it's going to be insanely expensive. If I calculate, so 10, right? 100th marker produced, so 98, 99, 100. The 100th unit that came along on that conveyor belt, that particular unit needs to have a smaller marginal cost than the ones before that. 1,000th needs to have a smaller cost, and 1,000,000th and so on. They all need to have smaller cost than those first markers that came out. Remember, if I'm going to make 1,000,000 of these markers, right? And the machine that is putting this together cost me $100,000. Well, the first marker that emerges, and then let's say machine breaks, and you say, I'm not fixing it. Well, what's the cost of that one marker then? Exactly. It's the entire machine plus the materials that went into the marker plus the design plus everything goes into that single unit that is produced. Right? Everything, yes. So you would probably be selling that marker for $500,000. This is the only one we make, all right? On the auction. As you sell 10,000 markers, 20,000 markers produced, 50,000, 100,000, right? 100,000 markers, $100,000 machine. You're not breaking even yet because there is design, there is electricity, there is transportation with a truck, right? And all of the other stuff that that it's there for the production.
Yeah.
So let's take a look at, I really like the example that it's given here. Cost function C of x is given as negative 0.02x squared plus 50x plus 100 for the first 100 items produced.
Oh,
So now we would like to know the average cost. Well, that's going to be our Cx divided by x, which is simply negative 0.02x plus 50 plus 100 over x. And we would like to know the marginal cost, which is C prime. And that one is the derivative, which is negative 0.04x plus 50.
I see.
So now I'm going to do the cost analysis of producing 100. Sorry, this is for the first 1,000, not the first 100. First 1,000 units.
First 1,000 units?
Yeah. So now I'm going to take a look at the cost of the average cost to produce 100 units. Good effort. So average cost at 100 units. Well, we'll use the average cost equation. That's going to be negative 0.02 times 100 plus 50 plus 100 over 100. That's negative 2 plus 50 plus 1, which is $49 per unit. On average, it costs me $49 to produce each unit of whatever the hell I'm making. Let's say I'm making these markers. Each one of these markers is going to cost $49 on average to produce for the first 100. This is a good number to know, because if this is all you're going to produce, you want to set your price at higher than that. Yeah, at what?
Yeah.
Because it's going to go to the stores from there. You're not directly selling these. So what are you selling this for to the stores? We have our business representative here.
Something. Sorry, I kind of
Yeah.
zoned out for a second.
So what price, guys? What's the percent? What's the markup to go out? 25%.
Yeah, something like 60.
So you just asked me
60%. There's the business major right there. 60%, yes. So, yeah. So you would be adding about $12, $13. So no, about $23 on top of this to go out. Generally, when you go to retail, you should be paying double the price of what it is to produce. There's too many hands in between. Now,
Okay.
so the first calculation was the average cost for the first 100 units. Now I want to see what is the cost of producing the 100th unit. Remember, single unit number 100. On the conveyor belt, there was a first unit, and then the second, and then the third. You went all the way to the 100 unit coming out. What is the cost to produce that unit?
$46.
$46.
Negative 0.04, multiply that by 100, you get negative 4 at 50, that's 36.
So $46 for that unit. Does this make sense? Of course it does, because the average cost was the average cost, right? And now we have the 100 unit. Well, that better be less than 49 if everything is working well in our business. Now we're going to move to the 900 units, check the average, and then check the marginal. For the average, we have negative 18 plus 50 plus 1 divided by 9 is about what? Very good. Yes?
I was just saying, like, a marginal cost curve that looks like a thing goes up after a certain point. So, like, isn't the thing that you said it's going to be, like, a straight line down, but it just starts at 50? What about the, like...
I'll have to take a look at that later. So, negative 18 and 50, that's 32. We have cents. It's money, right? So it's 11. So 32.11. Does that make sense? Yeah, because to produce 100 units, it was 49 cost. Remember, you are not buying a new machine. It's the same machine that you already paid for. So you produced 9 times more, and the cost went down per unit to 32.11. And now we have negative 0.4 times 900 plus 50, that's negative 36 plus 50 sits at $24 a unit. So that's what I said. Please pay attention. It's clearly 14. Look. It's 14. That's 14, right? That's okay. You're forgiven. I know. Thank you. So $14 per unit. So 900th unit that came up on the conveyor belt costs us $14 to make. And from this calculation, you see that the more units you make, right, the cost of production of each unit goes down. Now, there are other factors that can mess this up, because the machine might break, and then you need to fix that, and that can cost $30,000, right? The truck might break to the way to the warehouse, right, from factory. There are a lot of things that can go wrong, and you have to account for all of those things, and you have to have money in the account ready to deal with those things as they come up. It's not like you cash the first check and you go buy a yacht right away. So we see now the difference between the average cost, which computes on average the cost to make X amount of units. For 100, the cost was 49 per unit on average. For 900 units, the cost was 32.11 per unit. And then we looked at the marginal cost, which is that instantaneous, the derivative stuff. Marginal cost for particular unit, and then we picked the 100 and the 900 because we need to make sure that those numbers are smaller than the averages, because if this number is larger than the average, that's a problem, because through the time, your single unit, right, as you move away, costs you more to produce. Well, that's not profitable. So now you see that, if you're running a little bakery, you don't need to worry about marginal cost, because if you are making 30 donuts a day, you really don't have to worry about 30th donut cost and so on. even if you're going to do 100 donuts in your, your little store. But if you are a company that is going to make, 3,000 cars, well, you might want to do this comparison, right? If each unit is supposed to go out and be sold for, let's say, $50,000, right? And all of the things that can go wrong with the product that you're making. So this lecture was on derivatives as rate of change. And hopefully you understood that there are two ways to measure change. One way is to use algebra, which was secant line, which is your good old slope of the line calculation. Your y2 minus y1 over x2 minus x1, and we call that average. I don't care whether it's average cost or average velocity. It's the same concept applied to different situations. And then the second one that we consider is instantaneous change, which is the derivative, and that one measures the instant in time. If you want to know your velocity at the instant of time, you quickly glance at your speed, right? As soon as you see the light's reflection in your rearview mirror, right? That's the first thing you do. You check the speed. Now, you don't stare at it for 25 minutes to determine anything. It is whatever you quickly glanced at. That's the speed that you are going at in that moment, and that's what the derivative calculates. There are other examples. Another example that it's worth talking about, since we still have 5 minutes, is the example of population. I like that example because you guys talked about at least the bad model of population with the E.
Yeah.
What I can calculate now is I can calculate how much the population increases in time as we are going forward. So if you go and type in population clock, and you go to the .gov website, you will have United States data and the world data. It is using mathematical models to predict to the best of its ability current population of, as you can see on the left, United States, actually on your right, no, on the left, United States, and on the right, world population. It also gives us the most populous countries, number 1, China, and then India. United States comes in at third at 331 million. Now, other countries, Indonesia, Pakistan, number 5, Brazil, number 6, Nigeria, number 7, most populous country, Bangladesh, Russia, and last year Mexico overtook Japan. Japan is
Yeah, I hear they're on the.
Japan is dying rapidly, and they got woke, and that's it.
They got what?
They got woke. You never heard that?
They got what?
Okay, look it up.
Oh, they went broke. Oh.
No, I'll explain later. So they have no babies, okay, because everyone is busy working.
Oh.
Okay, good. So what you can do now is on this website, you can take a snapshot of the current situation of the world's population. You will say P, which is your x-coordinate, is 2019 and you pick 7.58, all right, as the world population. Then you type in world population in, I don't know, 1989, so you have, 30 years, and it will tell you the world population. You can use those 2 points to come up with the exponential model. You can use the lousy one, it's okay, on the short term. Now, once you have your population model, guys, I don't have time to go to calculations, but I can at least talk about it. If you have your population model, let's say P of t is equal to whatever, some initial population e to the kt, where this P0 and k would be known. The higher the k, the faster the growth in population. The lower the k, the slower the growth of populations. Population is dying out when k is negative. We call that decay. Now, you can take the derivative of this and you can observe the change of population in time, because this will be P0k e to the kt. So now you see that larger positive k will be changing the population in a positive fashion, making sure more and more and more population is added as the time goes on. For the declining populations, like the one of Japan and Germany and us now, actually, for the last 2 years, we are going to have negative k, which brings here as a negative, and then gives you negative change, which means population is decreasing over time, right? So mathematics, obviously, and these formulas, including derivatives and average change and so on, can detect all of those things. And that's it. I will see you all tomorrow.